Okay. The next example, the problem statement asking you to find the solution of this differential equation while x equals to 0. So from this, the first thing that we got to do is just we got to define whether x equal to 0 is the ordinary or singular point by finding px and qx. Okay, and from that we know that our px is equal to minus 1 over x and our qx is equal to 1 minus x divided by x squared, x to the power 2, x to the power 2. Now if you put the value of x equal to 0 for both px and qx, you would know that both px and qx is not an analytical solution, so that means x equal to 0 is a singular point. And then in order to find the solution while x equal to 0, and we know that x equal to 0 is a singular point. So what we got to do next step is just that we find whether it is a regular or irregular singular point by finding the value of x minus x0 px and x minus x0 to the power 2 qx. If you plug the x value equal to 0 in there, and if it makes both functions, it's not an analytical function, so that means it is an irregular singular point. Okay. From that, we would get that our px is equal to minus 1 and our x squared qx is equal to 1 minus x. So if you plug the value of x equal to 0, then it makes these two functions to become an analytical solution. So that means x equals 0 is a regular singular point. So from that we know that in order to find the solution, because we assume that y is equal to summation of an times x minus x0 to the power of n plus r, where n is starting from 0 to infinity. And if you want to know like which case that we would get, so we could find the value of r, you can use the initial equation, which is, in that case, you get to find p0 and q0 that you can use from the limit of this function. From that, you would know that vp0 is equal to minus 1 and q0 is equal to 1. And then you plug the value of p0 and q0 into your initial equation. In that case, you would get the value of r. When I plug the number in, I would get this. So from that, the equation would be in terms of r to the power 2. So that means you can find two values of r. Now, I get the value of r is equal to 1 and 1. So that means r1 is equal to 1 and r2 is equal to 2, which is to 1, which is r1 equal to r2. It is in our second case. For the second case, we say that y1 should be in the form of summation of an x plus 1, x to the power of n plus 1, n starting from 0 to infinity, and y2 is equal to y1 ln x minus x0. Now x0 is equal to 0, so you get y1 ln x. And the second term is summation n starting from 1. Here, n starting from 1 to infinity of bn times x minus x0 to the power of n plus r1. Now our x0 is equal to 0, so you would get bn x to the power of n plus 1. Now, because you know that your two solution would be in this form. Okay, so now we are going to write that in such a way that we can get the recurrency relation. So from that, I say that we assume that y is equal to an times x to the power of n plus r. Okay, and then we do first derivative and second derivative of y, and then we plug it back into our differential equation. After we plug it in there, we would get this term, we get the term of that, right? And then we have x squared here. We just combine this x squared to the x to the power of n plus r minus 2. So we would get x to the power of n plus r. And this term you have x there, you put x back, combine it with the term of x to the power of n plus r minus 1. So you would get x to the power of n plus r. This one, you have two terms, right? First term is summation of an x to the power n plus r. And the second term is minus x times summation of an x to the power n plus r. Now your x here combined with term of x to the power n plus r, you got x to the power n plus r plus 1. Now, these three terms have the same power of x. You combine them together. So you would get this. After the combination of these three terms, you got only one big term here and that term there. Now, are you going to shift the index of x to the power n plus r to be n plus r plus 1, or you are going to shift the n plus r plus 1 to n plus r? You are going to shift the index of n plus r plus 1 to n plus r by replacing this one equal to n minus 1. Okay. We are doing that. This term you got n minus 1 equal to 0, an become an minus 1, and x to the power of n plus r plus 1 becomes x to the power of n plus r. Okay, and then n minus 1 equal to 0, so n is equal to 1. This term n starting from 1, but this term, now we have the same power of x, but this term starting from 1, this term starting from 0, you just cannot combine them together unless this term starting from 1. So in order to get that, you plug n equal to 0 in there. You would get r times r minus 1 minus 1 plus 1 times a0, right? Because you put 0 there, you would get n a0, r to the power x to the power r, because n equal to 0. And the rest of the term we can write down in the term of summation. And this is just the term, we didn't do anything with it. Now, this term and this term, they all look the same now. Now you can combine them together, both of the power of x and the starting point of the n. Now you can combine them together, so you got this term. But with this one, x to the power r, like I said, we are going to use the comparative of the coefficients. If you notice it, you would see that the term inside the parenthesis here is the integral equation, right? It is exactly the same as the integral equation. So if, like I said, you don't need to use the formula to find the value of r. If you are quite sure that the process that you are doing from the beginning up to this point is right, you can take this as a integral equation. Okay? Now, from doing comparing of the coefficients, we would say that the term of r times r minus 1 minus r plus 1 equal to 0, and that is giving us the value of r, which is, and we know that it would be the same value. R1 and R2 would be the same value. Okay, we already did that. R1 equal to 1 and R2 is equal to 1. We got 1, 1. Okay, and the second term, we are going to get the Lagrange relation, right? So the term inside the parenthesis is equal to 0, where n is greater than 1, equal or greater than 1, got to starting from 1 until infinity. And from that, you would get an is equal to an minus 1 divided by n plus r times n plus r minus 1 plus minus n plus r plus 1. You plug the value of r is equal to 1 in there. You would get an is equal to an minus 1 divided by r equal to 1. You would get n plus 1 here, n there, minus n plus 1 plus 1. Right? Just plug the value, nothing else. And then you combine the term together, so you would get an is equal to an minus 1 divided by n squared, where n is greater than 1, equal or greater than 1. And then you just try to find the sequence of a. So you plug n equal to 1, 2, 3, 4, 5 to see the radium of it, and then as you plug n is equal to 1, you find the value of a1. a1 is equal to a0 divided by 1. a2 is equal to a1 divided by 4. a3 is equal to a2 divided by 9. Right? And a4 is equal to a3 divided by 16. 16 is 4 times 4. 9 is 3 times 3. 4 is 2 times 2. 1 is 1 times 1. So you have two groups of the number, which is 3 square. For this one, you got 2. 2 times 2. This one, you got 3 square times 2 square, or you get 3 times 2 and 3 times 2, which is 3 factorial and 3 factorial. This one you got 3, 4, 4, 3, 2, which is 4 factorial. This one you get 4, 3, 2, which is 4 factorial. You got n factorial times n factorial, right? Which is n factorial squared. So I would say that then at the end I would get an is equal to a0 divided by n factorial squared. Right? If you see the radius, you know that a1 is equal to a0 divided by 1. 1 is just 1 times 1. a2 is equal to a1 divided by 4. 4 is 2 times 2. Right? But a1 is equal to a0 divided by 1 times 1. So you have two sets of the number. This one you would say that you have 2 times 1 times 2 times 1. Now, a3 is related to a2 divided by 9. 9 is equal to 3 times 3. But a2, your a2 is equal to a1 divided by 2 times 2. And your a1 is equal to a0 divided by 1 times 1. So I just rearrange it in such a way that, because I know that we have 3 and 3. And we have 2 and 2, and we have 1 and 1. So I just put them together because I know that 3 times 2 times 1 is equal to 3 factorial. So it seems like you have 3 factorial times 3 factorial. Right? And this one, it just seems like you have 4 factorial times 4 factorial. And then when you plug n is equal to 5, you've got like 5 factorial times 5 factorial. Now, if you have n times, you would get n factorial times n factorial, which is equal to n factorial to the power 2. Now, the first answer, it says that summation an x to the power of n plus r. Now your r is equal to 1, you just put the number of r there. N starting from 0 to infinity. So that means if you put n is equal to 0, you get a0 x to the power of 1. Right? If n is equal to 0, you got x. If you put n is equal to 1, you get x to the power of 2. If you put n is equal to 3, you got x to the power of 4. And so on. Now, you plug the value in there. a0 x plus a1, you know it's equal to a0 x to the power 2. Now, your a2 is equal to a0 divided by 2 factorial squared times x to the power 3. And a3 is equal to a0 divided by 3 factorial to the power 2. and so on. And then from here I said that, oh, we have every term have a0 and x, so we take a0 and x out. So you would get 1 plus x, right? Take a0 out, this term you have 1. Plus a0 x out, you got x. a0 x out, you got x to the power 2. a0 x out, you got x to the power 3, right? Now, inside here, it can write out in the term of summation. You would get x to the power n divided by n factorial to the power 2. If you put n equal to 0 there, you would get 1. If you put n is equal to 1 there, you would get x. If you put n to the 2 there, you get x to the power 2 divided by 2 factorial there. If you put n is equal to 3 there, you got x to the power 3 divided by 3 factorial to the power 2. See? Now, this is y1. y1 is off that. But for y2, how do we do that? We just cannot put the value of y2 like, we just cannot put the value of r to find the recurrence relation to get the second set of your Bn, because now your r is the same. If you write it down, it's going to be the same. So the two answers should be linearly independent. If it's the same, so it's not linearly independent. So that's why they have to give you the second solution, which is different from the first solution and linearly independent. How do you find Bn of y2? You've got to plug y2 into your differential equation. But for y2, there is a function of y1 there. So now you know the function of your y1 already. So you can find the recurrence relation of your Bn. The way that we do that is just by doing first and second derivative of your y2, and then plug y2 and their derivative into your differential equation. And we do that. Here, we put the second derivative, first derivative, and y2 into differential equation, and we got this equation. It's very long because the result of the second and first derivative is quite long. And the rest of the term, what we do is just that we rearrange in such a way that we can find the rhythm of it. And then if you rearrange it, you would see that some term just go to 0 from the meaning of the equation itself. And by doing that, so this one is just rearranged, okay? The way to do from this one is just plugging the first derivative, second derivative, and y2 into your differential equation. This one is just doing the rearranges in such a way that make the equation simple. But if you can see that this one is the same equation, okay? No, this one is here, and then I just distribute the terms of x squared into every term there to get this line. And after I get this line, the term which is look the same, for example, minus y1 and minus y1, just combine them together to get minus 2y1. Minus 2y1. Okay? And then any term that you can combine them together, you just combine them together. But this one, I just try to rearrange in such a way that it is getting like the differential equation itself, because it's saying that here, x squared times second derivative of y minus x times the first derivative of y plus 1 minus xy equal to 0, right? So this term I rearrange in such the way that I can get this relation, and I know that it's equal to 0. So 0 times ln x equals to 0. So I can cancel out all these terms. And then after that, I rearrange the differential equation again and try to combine the term together. But these two terms, I just cannot combine them right away, although their n value is starting from n the same. But I still cannot combine them together because the index of each term is still different. So I'm going to do the shift of index from that. So I have n plus 1 and n plus 2. Should I do n plus 1 to become n plus 2, or should I do n plus 2 to become n plus 1? We should do x to the power n plus 2 to become n plus 1 by replace this n equal to n minus 1. By doing that, I get b minus 1. And here is n minus 1, and this one we got x to the power of n plus 1. Okay? Now, and then n minus 1 equals to 1, so n is equal to 2. Right? And then these two terms, although the index of x is the same, but we still cannot combine them together because now this n is starting from 2 and this one starting from 1. So we got to change this one to be starting from 1.